Hello my shimmering stars, today I Shaurya Grover welcome you all to this amazing platform of PW Gulf. So students, today I am going to start with your new chapter, that is the solid state, under your batch, Triumph batch. So students, you all are aware that we are basically doing the summary session, that means the ultimate recap session. So we are going to revise the complete chapter of yours in this particular session today. We are going to revise the complete solid state chapter, and I guess you all are ready. So students, if you have not ever heard a single word with regard to this chapter, or you have any problem in any of the topic with regard to this chapter, I assure you that after completing this session, it will be clear. So what you need to do is, you just need to take a copy and a pen and just sit down and just understand each and every concept and make your quick notes with the help of this session. As you all know, this is your ultimate recap. So you are going to make the quick notes that you can revise during your examination. Okay, because it is a kind of a summary, it is a kind of a revision section that we are going to do. Now, how are we going to proceed, or what are the important topics, ma'am, that we need to cover during our examination? So see students, first of all, how we are going to proceed in this particular class, let me make you aware of it. First thing that we are going to do is, I will tell you that what is the today's target, how we are going to proceed, which is your first topic, then the second, then the third one. And after that students, before starting your very first topic, I will let you know the most important topics from which till now, a maximum amount of questions are being asked. Though I will be completing each and every topic of yours, but yes, it is important for you to know that in the previous year question papers, which are the topics from which questions are asked. What are the topics? Okay, so I'm going to tell you that also. Moreover, students, all the calculation works and all the formula, we are going to write it over here so that you can prepare your formula sheets. So everybody be prepared for this particular session. Before starting this, there is a wonderful quote, students. Teachers can open the door for your opportunities. Teachers can open the door for your opportunities, but it is only you who have to move forward. It is only you who have to move forward. So students, be prepared for the wonderful opportunities that you are going to have. Grab it and move forward, students, but with a beautiful smile. Yes? Okay, ma'am. So how we are going to do this? I welcome you all to your Triumph batch yet again. See students, the very first topic that we are going to start with is going to be the introduction to solid state. In your class 12th, basically, this is your first chapter, the solid state. But in your class 11th, you have heard about states of matter. Not only in class 11th, but in your lower classes also, you have heard about solid, liquid, gaseous. But here in this particular class, in this particular chapter, we will focus upon the solid state. Moving further, we will understand about the types of solid and the crystalline solid. See, solid are further categorized into two classes, and there also are further classified into further types. Okay. The third part that we are going to start will be about crystal lattice and space lattice. Wonderful 3D imaginative topic. You are going to enjoy this chapter to a greater extent, students, because this is a 3D imaginatory chapter. Moving on to the next one, we have types of lattice, students. The next part that we shall be covering will be about unit cell and its types. Very, very important. Very, very important, everybody. Do pay attention on this topic because this is the basic for your chapter, the solid state. Moving further, we will understand about the number of atoms in a unit cell from which maximum, questions are being observed. So yet again, this is an important topic. Moving on to the next one, we will be understanding about closed packing in 1D, 2D and 3D. The next part will be about types of voids. Now, what is voids, ma'am? This is a new word. Void is basically the empty space that we observe when atoms are joined together. So we shall be understanding about them as well. Moving on to the next part, we will be covering ionic solids. And then the different crystal structures in ionic solids. Then will be packing efficiency and cell dimensions. Yet again, the most important topic from which you are going to observe a lot of questions. And then we are going to see the defects in solids, again the important one, theoretical topic, imperfections in solid. But it is important as well. So now, as I've told you, I have already said you before starting the session that I will be telling you what are we going to cover. Then I will be informing you about the most important topics. So let us see what are these topics. So these are the most important topics that you have to, students, you have to do before going on to the examination. You don't have to skip these topics repeating again and again. Why? Because from last so many years, maximum questions are being asked from these topics, guys. Maximum questions. Okay. So the maximum questions are asked from calculation involving unit cell dimensions. Then questions are being asked from imperfections in solid. Okay. After that, you shall be observing questions from number of atoms in a unit cell, and the last one is crystal lattice and the unit cell. So these four important topics, if you are going to see in a sequence, it is starting like this: crystal lattice and unit cell, then comes number of atoms in a unit cell, then comes calculation segment where you are going to observe about edge length, about radius, about density, about packing efficiency, all of that stuff. And at last, it is imperfections in solids, that is defects in solids. So I guess now you know how the criteria is going on. Though I will be explaining you each and every topic which I have already told you in today's target. We are going to cover these 12 topics over here. But yes, these 4 are really very important from these 12. They also are, but these 4 are very, very important. So starting with the very first topic of our students, what do you know about solid state? My question is, what do you know about solid state? You will say, ma'am, till now we have heard about ice, form of water, ice, it is solid, right? So when we see water in the liquid form, it is liquid. When we see water vapors, it is gaseous form. So we know solid is basically something which has an arrangement, a kind of an arrangement where particles are closely packed. Okay, you are somewhat close to the definition of solid state. Yes, you are. What is a solid object? In solid object, students, you will observe that there are particles which are closely packed to each other. Now, before coming to this part, let me tell you there are 2 forces that are taking place. The very first force that you may be observing will be force of attraction. And the second force that you should know is the force of repulsion, or the tendency to escape from each other. Yes, you heard it right. There are 2 forces, force of attraction and force of repulsion, right? Now, these 2 forces are responsible in order to do the classification of states of matter. Because of these 2 forces, we classified matter into solid, liquid and gas. Now, what happens in the case of solid, ma'am? Let us draw. In the case of solid, what you are going to observe? See, for example, this is first particle, second particle, third particle, fourth particle. Your next layer. The next one over here. So what are you observing? What are you observing? If I say this is your first particle, students, this is your second particle, just tell me, is first particle far away from the second one? No, ma'am. They are so close to each other. They are like this. That means there is a strong force of attraction between the particles. Force of attraction, in other words, is good bonding, I would say. And what is force of repulsion, ma'am? Bad bonding, I would say. Not a good one. Let us say you have your good friend. So when you have your good friend, you discuss all your problems with your friend. That means you have a good bonding. But let us consider an enemy of yours, or the person in your life who never wants you to move forward. The one who demotivates you is the one with whom you will feel like, I should stay away, right? We should stay away from the negative people, from the negative vibes, right, guys? So that staying away basically is what? Force of repulsion, or the tendency to escape from each other. So in the case of solid, do you feel there is any force of repulsion or tendency to escape from each other? No, ma'am. But there is very, 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 very less amount of force of repulsion. But there is a strong force of attraction, students. Very strong force of attraction. So over here, what I'm saying is, in solid, you are going to observe strong force of attraction, but very, very, very less amount of force of repulsion. So let us see, the particles in solid are closely packed. They are closely packed, tightly packed, and held together by strong intermolecular forces. So this is going to be the definition. If I'll talk about the properties of the solid state, students, what do you feel? What are the properties of solid state? See, one by one, let me tell you. They have definite shape and volume, first of all. See, this basically definite shape and volume. If we were differentiating with liquid and gaseous, there was no definite shape but a definite volume in liquid. In gaseous, no definite shape, no definite volume, right? So this basic property each and every one of you knows. We'll talk about the next one, that is solids have high density, high density. The next is solids have high melting point, and the last one is solids, they show very slow diffusion. Let me tell you students, if I'll talk about the movement of particle from one place to another, in the case of solid, they vibrate along their mean position. The particles are, it's a very rare chance that they are moving from one position to the another, because they are so strongly attached to each other, they usually vibrate along their mean position. These were about the properties of the solid state. Let me discuss you with regard to the types of solid, students. What do you feel? What are the types of solids? See, solids are further categorized into two types. One is crystalline solid, another one is amorphous solid. What I'm talking about is crystalline solid and amorphous solid. What do you feel? What is crystalline solid? Ma'am, crystalline solid is the one in which there is a regular arrangement of particles. And amorphous solid is the one in which there is an irregular arrangement of particles. How, ma'am? Let us see with the help of example. See, in the crystalline solid, let us consider we have made a solid object with two kinds of particles, A particles and B particles. So let us understand the arrangement, students, quite clear over here. It is A, then comes your B, then comes your A, then comes your B. See, this is a rough structure, okay? This is just a random structure which I have drawn. See, what are we observing over here? There is a regular pattern. It is A, B, A, B, B, A, B, A, A, B, A, B, B, A, B, A, A, B, A, B, B, A, B, A, B, A, B. What are you observing? You are observing that, ma'am, there is a regular arrangement of particles. There is a regular arrangement of particles, ma'am. But what happens in the case of amorphous solid? There is a irregular arrangement of particles. How irregular, ma'am? For example, this is your A, then B, then your A. Now B should come, but B won't come. A will come. Let us see over here. A, B, A, B. Here A, here B. Now A should come, but A is not coming. It's B again. Here B should come, but A is coming. Here B should come, but A is coming. So what you are observing, that when you are moving at a distance, the arrangement breaks. There is an irregular arrangement of particles. So that is amorphous solid. That is what is amorphous solid. Let us see it with the help of more such images. So this image you can clearly observe. This is a crystalline solid which has a regular arrangement of particles, and amorphous has an irregular arrangement. Moreover, students, over here, crystalline solids are anisotropic in nature. Anisotropic in nature. And if I am talking about amorphous solid, it is isotropic. It is isotropic in nature. Now, what is anisotropic and isotropic behavior? See, iso refers to as same. When we have different physical properties, but when we move in different directions, it remains same throughout. Same physical properties in different directions, that is isotropic. But different physical properties are obtained in different directions, that is anisotropic. Clear, guys? Clear? So now, let me tell you what, let us take an example, a general example. You all have seen the old buildings, right? Now, just look up to this image, this video over here. You will automatically get to know what I am talking about. You can clearly see the glass that you are observing. This is a window plane, right? A window, the glass window. This is window, this is the glass of the window. Now students, just tell me why it is thick at the bottom and thin at the top. What is the reason behind it? What is the reason behind it that it is thick at the bottom, thin at the top? That means what? Glass is a kind of a solid. My first question to you all is, students, my first question to you people is glass an amorphous solid? Ma'am, amorphous solid, glass, you are saying glass is thick at the bottom, thin at the top. Yes, students, glass is an amorphous solid. It exhibits the properties of amorphous solids. Okay, ma'am. Now, my next question to you is glass pseudo-solid? Ma'am, pseudo? What is pseudo, ma'am? What is pseudo, ma'am? Pseudo, in other words, is fake, students. For example, if I say pseudo smile, that means I'm smiling in front of you, but from inside I'm not happy. For example, if I'm saying pseudo happiness, that means I'm spreading pseudo happiness, a fake happiness everywhere, but I'm not happy from inside. Pseudo means fake. Pseudo solid. That means it do have some characteristics of solid, but it also have some characteristic of another state of matter. So yes, glass is a pseudo solid. So why, ma'am, why you said glass is a pseudo solid? Because glass is a super cool liquid. You will say liquid? How, ma'am, liquid? Because glass has a tendency to float, students, and if it has a tendency to float, that's why it becomes thick at the bottom and thin at the top, because it flows. So yes, it is also referred to as super cool liquid. So you very well know now that if we are talking about amorphous solids are pseudo solids, amorphous solids are also referred to as super cooled liquids. Clear, guys? Okay, starting with now types of crystalline solid. Now we know what is crystalline, we know what is amorphous. We are going to understand about the types of crystalline. Crystalline are further categorized into molecular solids. Okay, in molecular solids, the bonding is being observed between molecules. Then comes your ionic solid. Now, in ionic solid, the bonding is being observed between ions. Which kind of ions, ma'am? Which kind of ions, ma'am? Here, you will be seeing cations and anions. Cations and anions. Okay. If I talk about covalent solid, here covalent bonding is being observed. If I talk about metallic solid, students, here metallic bonding. Now, metallic bonding also will occur between whom? Will occur between kernels and free electrons. Kernels and free electrons. Let us understand all of them by depth. But for this, you can open up your NCERT or you can even write from here. This is taken from NCERT, students. Let me tell you, there are 4 types of crystalline solid. Very, very important, students. The one which I am going to mark, you have to put a tick over here or you can write it down. If I talk about the very first type, that is molecular solid, which is further categorized into non-polar, polar and hydrogen bonded. Now, non-polar are the ones which there are no poles. That means no positive negative charge. Polar ones are the one in which we have a positive and a negative charge. Then comes hydrogen bonded. Now, what is hydrogen bonded? When hydrogen is linked with hydrogen bonding to more electronegative atoms such as fluorine, nitrogen and oxygen. That is hydrogen bonding. Even hydrogen bonding is further categorized into intermolecular and intramolecular. Okay. Now, talking about non-polar, in non-polar constituent particles are molecules. Do remember, in molecular solid, constituent particles are molecules. In ionic solid, the particles that are showing bonding will be ions. In metallic solids, it is going to be positive ions, that is kernels, with delocalized electrons, that is free electrons. And at last, we have covalent or network solids. Over here, the bonding is being seen in atoms. Next comes is, in molecular solids, in non-polar solids, the kind of attractive forces that do we observe over here is dispersion or London forces. In polar, we have dipole-dipole interactions. Important yet again. Why dipole-dipole? Because positive and negative dipoles are created. Next is hydrogen bonding. We very well know is hydrogen bonding itself. Then comes in ionic, there is electrostatic or Coulombic force. Or we can even say force of attraction. Or we can even say there is a force of attraction, guys. And then in metallic solids, it is metallic bonding. And at last, in covalent, and it is covalent bonding. Covalent or network solid, it is covalent bonding. Talking about the examples of non-polar, we have argon, we have CCl4, we have H2, we have I2. Talking about polar, we have HCl, SO2. Talking about hydrogen bonding, we have water in the form of ice. Then in the case of ionic, we have NaCl, MgO, ZnS, CF2. And in the case of metallic solids, we have Fe, Cu, Ag, Mg, right? In covalent or network solids, we have SiO2, SiC, carbon in diamond form and carbon in graphite form. Now, let me tell you about the nature. See, in nature, non-polar and polar ones are soft in nature, but hydrogen bonding ones are hard in nature, okay? Talking about ionic solids, they are hard but they are brittle. Talking about metallic one, they are hard but malleable and ductile. Malleable and ductile, that means when you are, converting them into thin sheets and thin wires, right? Now, covalent bonding, basically we see carbon in diamond form is hard but carbon in graphite form is soft. Quite important topic. Carbon in diamond form is hard and carbon in graphite form is soft. Talking about the electrical conductivity, let me tell you, molecular solids are insulators. Ionic solids are insulators in solid state but conductors in the molten and aqueous state. Okay, talking about metallic, they are conductors in solid as well as molten state. While talking about covalent or network bonding, students, they are insulators. But yes, graphite again has an exception, it is conductor. Here melting point is, they have a very low melting point. Ionic will have high, but very high is being observed in your covalent or network solid. Yet again, very important part, students. Is it clear to each and everybody of you? Yes, everyone, please mark it so that we can move on to the next part of our today's class. Okay. Moving on to the next one, what do we have now? Crystal lattice and space lattice. First of all, let us understand about the word lattice. Or I would say the lattice points. Lattice points basically are the points at which particles are kept. At which particles are kept. Now, over here, the term particles stands for atoms, molecules, or ions. Okay, the points at which all of these are kept basically is referred to as your lattice point. Let us take a general example. As you can clearly observe, these are your points. At these points, we have kept these atoms. So basically it looks like this. So these atoms were kept at these points, right? At 8 corners I have kept. So basically this is lattice point. And when we keep atoms on it, it will create a crystal structure, that is crystal lattice. And when we are arranging them in all the directions in space, that is space lattice. So first of all, what do you refer to as crystal? This question generally is being asked. What is a crystal, guys? Not asked, I would say you should know about it. So yes, crystal basically, it is a homogeneous portion of solid substance, students, that is made up of a regular pattern of structural units bonded by the plane surface, making definite angles with each other. Let me write this lattice point definition over here. Yes, everybody, till then you can write it down. Clear, everyone? Okay. Moving on to the next one, you can clearly observe these were the particles. Okay. These were kept at these points. So these points over here is the lattice point. So now you can clearly know that how basically this structure will look. This structure is basically will look like this after keeping it onto these lattice points. Clear? Now you very well know what is lattice point, what is the structure, right, guys? Now comes the types of lattice. See, when we are going to divide lattice, it will further divide into 3 types. 1D lattice, 2D lattice and 3D lattice. Okay, now 1D, 2D and 3D. If I am talking about 1D lattice, atoms will be arranged in one dimensional only, either x-axis, y-axis or z-axis. Particles will be kept on single axis. For example, this is your x-axis, that means only one dimensional, so this is 1D lattice. Okay, either you can take y-axis also, you can take your z-axis also, as you wish, right, students? So if I'll ask you the parameter over here, that means what is the distance between these two atoms? So it is going to be what? It is going to be A. So the first parameter that we observe over here is going to be what? It is A, ma'am. Clear, guys? Moving on to the next one is 2D lattice. When particles are arranged in 2 dimensions, that is 2D lattice. So over here, if I am referring to as 2D, it is either XY or YZ or ZY, right? So that means if I am saying this is your x-axis, particles are arranged in x-axis as well as on the y-axis. So this is your 2D lattice that you basically can draw on your sheets, right? So first of all, what are the parameters that you observe? See, the distance between these two atoms is A. on the x-axis 1. Similarly, on the y-axis 1, the distance is going to be b, let us consider. And the angle between both of them is alpha. So, how many parameters do you observe over here? The parameter that you are going to observe is A, B and alpha. A is basically the distance of atoms on the y-axis, distance between two atoms on the y-axis. B is basically the distance between two atoms on the A is on the x-axis, B is on the y-axis, and alpha basically is the angle between A and B, right? So, the very first type of 2D lattice comes out to be your square unit cell or square lattice. See what happens in this case. In this case, it is very easy. Here we have A, B and alpha. So, here in this case of square, A is equals to B and alpha is equivalent to 90 degree. See how? See, this is your A, the distance between these two. So, it is A and this is your B. The distance is same for both of them and the angle between both of them is 90 degrees. So, when you are going to join it, students, it forms a square shape. So, this is square unit cell, square 2D unit cell. And when you are going to repeat this, for example, if you are going to repeat this particular structure again and again, so, you are going to obtain what? You are going to obtain a bigger structure. So, this is what is a types of lattice. This is about square lattice. This is about square lattice. Second comes your rectangular lattice or rectangular unit cell. In this case, A is not equal to B, but yes, alpha is equivalent to 90 degree. Let us see how. If this is your A, the distance between these two is greater in comparison to the distance between these two on the y-axis, but angle is 90 degrees. So, when you are going to join it, it forms a rectangle, and this rectangle when on repeating will form a bigger structure. So, this is rectangular lattice. Right guys, moving on to the third type, we have parallelogram. We have what? Parallelogram. In the case of parallelogram, you can clearly see this is your A. This is your B basically. Here you can clearly see that alpha is not equal to 90 degree guys. Alpha is less than 90 degree. In the case of rhombus, next is rhombus. This is parallelogram. Rhombus basically will look like this. Just a kite-like structure. So, this is next the type of square, next the kind of, I would say, the crystal system. Last 2D lattice type is going to be hexagonal because it forms a hexagon. It forms what? A hexagon. And when you are going to repeat this hexagon, you are going to form a bigger structure. For example, if you are going to repeat it, see, if you are going to repeat it, a bigger structure is going to be formed over here. You are going to obtain a wider, bigger crystal structure. Clear guys? Clear guys? Okay. So, now students, this was about types of 2D lattice. Now comes the types of 3D lattice. Now, in 3D lattice, you have 3 dimensions: x-axis, y-axis, z-axis. On x-axis, you know A distance. On y-axis, you know B distance. On z-axis, it is C distance. Alpha, beta, gamma are the angles between them. So, basically, there are 7 types that you are going to observe in the 3D pattern. There are 7 types. What are these 7 types, ma'am? Cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, rhombohedral. How are you going to learn them? There is a trick for them. What is the trick, ma'am? What is the trick to learn them? That is cute our mother. Cute our mother is your trick basically, students. Cute our mother is your trick. How come? Let me tell you. CU stands for cubic. CU stands for cubic. CU stands for what, ma'am? CU stands for cubic. Now, what is the next one? TE. TE stands for tetragonal. TE stands for tetragonal. Clear? Then comes R. Then comes what? R. R stands for orthorhombic. R stands for orthorhombic. Clear? Then comes MO. Then comes what, ma'am? MO. MO stands for monoclinic. MO stands for monoclinic. Yes, guys. After this, students, we have T over here. This T stands for triclinic. This T stands for triclinic. Then we have what? Then we basically have HE over here. We have HE, that stands for hexagonal. That stands for hexagonal. And at last, what do we have? We have R over here. And this R stands for rhombohedral. Rhombohedral. So repeating again, the trick is cute R mother, cute R mother. CU stands for cubic. TE stands for tetragonal, R stands for orthorhombic, MO stands for monoclinic, T stands for triclinic, HE stands for hexagonal, R stands for rhombohedral. Now, how you are going to do it? See, first of all, write unequal parameters. This is just a trick. This is just a trick. You are not going to observe it in any of the books, okay? So, write the value 0, 1, 2. From below also write 0, 1, 2. 1 is left, just write 2 over here. So, it is 0, 1, 2, 0, 1, 2 and write 2 at the center. Now, what's next? You have to write axial lengths. That means about A, about B, about C. 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 About A, B and C you are going to tell. Again I am telling A is the distance of atoms in the y-axis, distance between two atoms on the x-axis. On the y-axis it will be B and C on the z-axis. Now write equal to sign in all of them. Write equal to sign in all of them. Everybody, I guess everybody has written them. Now, after this, ma'am, what we have to do? Very important. See, there is 0 unequal parameters. That means this is the value for this. There is one unequal parameter. From the right hand side, put a dash. That means put an unequal sign. Now, there are two unequal parameters. 1, 2. Next, 2 unequal parameter. 1, 2. Now, next, 2 unequal parameter. 1, 2. Now, 1 unequal parameter this. 0 unequal parameter this. I guess everybody knows this now. Now comes your interfacial bond angles. That means about alpha, beta and gamma. See, in the case of cute R, that means cubic, tetragonal and orthorhombic. The values for cute R will remain that alpha is equals to beta is equals to gamma is equals to 90 degree. The values for cute R will be this. So that means for this also it is alpha is equals to beta is equals to gamma is equals to 90 degree. For this also alpha is equals to beta is equals to gamma is equals to 90 degree. For these three the value is going to remain same. Now comes the most unsymmetrical, that is triclinic. It is most unsymmetrical. So over here alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. If I talk about rhombohedral, it is alpha is equal to beta is equal to gamma, but all of them are not equal to 90 degree. First of all write them, then comes two cases that are left. Everybody first of all write them, then comes two cases that are left. Everybody written? Now in this case monoclinic, alpha is equals to gamma is equals to 90 degree, but over here students beta is not equal to 90 degree. Okay, also write over here in the case of triclinic, as I have told you, it is most unsymmetrical. And if they'll ask you about most symmetrical, so that is going to be cubic. Most symmetrical, that is going to be what? That is going to be, ma'am, your cubic, because see, A is equals to B is equals to C, alpha is equals to beta is equals to gamma is equals to 90 degree. Each and every part over here is going to be same. Clear? Now, in hexagonal, alpha is equals to beta is equals to 90 degree and over here gamma is equals to 120 degree. So this completes our types of 3D lattice, students. But yes, one thing is still left. Everybody first of all write it down. Written, guys. Now see, these are also further categorized into Bravais lattice. These are crystal system. They further categorized into Bravais lattice. See, cubic basically is further categorized into three types. It will form three structures: simple, face-centered, body-centered. Tetragonal basically will form two structures. So if you are going to add all of them, see what value comes. It is 3 plus 2, 5, 5 plus 4, 9, 9 plus 2, 11, 11, 12, 12, 13, 13 plus 1 is 14. So total 14 Bravais lattice are obtained from the 7 crystal structures. And one more question they ask you generally, which of the following forms the maximum Bravais lattice? That is orthorhombic, which forms 4. Clear, guys? Okay. Now students comes unit cell and space lattice. What is unit cell and space lattice? See, for example, if you have to make a building, in order to make a building, first you will make a wall. How are you going to make a wall? You are going to take a brick, you are going to repeat that brick, and on repetition that will create a wall. right? So this is what is a unit cell, which on repetition will form a crystal lattice. Let us understand in depth about what? About unit cell. It is the smallest portion of a space lattice, which when repeated in different direction creates an entire lattice. Let us take a general example. For example, this is our cubic lattice. Now only we have done in 3D. First type is cubic lattice. Cubic lattice is the one in which A is equals to B is equals to C, alpha is equals to beta is equals to gamma. This looks like this, okay? When I am repeating the structure again and again, see. When I am repeating the structure, it's forming a greater structure, a bigger structure. So this one structure which on repetition forms a bigger structure is what? Is your unit cell. It is what? It is, ma'am, my unit cell. Clear, everyone? Okay, now students, coming to this, see, you can clearly observe this diagram, what it is exactly. You have replaced particles and you have kept atoms on it, right? See, these are the lattice points. You have kept the atoms on them. Now, what is this type basically? This is your primitive unit cell. Before starting this, let me tell you, when you are going to classify unit cell, students, when you are going to classify unit cells, you will classify unit cells into two types. One is primitive unit cell. One is primitive unit cell. Another one is non-primitive unit cell. Non-primitive unit cell. Now, what is a primitive unit cell? When atoms are present at the corners. When atoms are only present at the corners, that is primitive unit cell. When atoms are present at the corners as well as at some other position. So that is your non-primitive unit cell. Non-primitive unit cell are further classified. But before making these unit cell, students, let me show you one structure. Let me explain you what are corners, what is face center, what is each and everything over here, right? Let us first understand about it. See, this is your home, guys. First of all, we are going to understand about what are corners, what is body center, what is face center, what are the edges, okay? Because I consider that each one of you should know about it, right? For example, this is your home, I'm considering. Now, I'm just putting some lattice point where your rooms are being kept. So, basically, this is your home and this is the building structure of your home, right? And let us consider that this is your room. This is your room. Let us consider this, okay? Now, this is you, students. See where this point, where his hands lie. His hands are like this and it is pointing towards like this. 1, 2. Now, what you have to do is stand up, my dear students. Stand at the center of your room. Stand at the center of your room. Consider your room to be square in shape. Say 1, say 2. Just as they both are blinking eyes, right? Now what you have to do is, the next part is, what you have to see is the boy standing straight but is pointing towards downward. 1 and 2. See the blink over there. So it's 1, 2, 3, 4. Now what are these 3, 4? These 4 are corners. Now observe the next part. This is basically, I am talking about the front view, right? Now turn yourself around like this. So see, it is 1, 2 lower now. See, this was your front face wall. Now this is your backward and this is 1, 2. Now see next part, it points at over here 1 and 2, 4 points. So basically see, at the front wall it is 1, 2, 3, 4. At the back wall it is 1, 2, 3, 4. Total 8 corners. Now everybody know what is corner? Okay. Let us, students, now understand about face center, body center, so that we can get an idea about it. But before that, first of all, let us see. Now, you know what is corners. So, these are the atoms that are placed at the corners of a unit cell. You know what are the corners of a unit cell? We will draw over here only. So, the very first type is primitive unit cell. Already told you, in the case of primitive unit cell, atoms are present at the corners. So, for example, this is your unit cell, students. Okay, cubic unit cell. Now, see, what are the corners? 1, 2, 3, 4, 5, 6, 7, 8. If atoms are kept on them, that will form a primitive unit cell. Let us take that structure also in order to explain you in more depth. You will clearly see these are the atoms. Clearly observe. So this is how the crystal structure look like. These are the corners, and when you keep atoms, it will look like this. So this is the primitive unit cell, guys. This is what? This is primitive unit cell when constituent particles are present only at the corner position of a unit cell. Now talking about the second one, see here. Atoms are kept at the corners as well as at the face center. So this is basically referred to as non-primitive unit cell. Now what about non-primitive? When atoms are present at the corners, but along with the corners it is present at a different position. So the very first type over here in non-primitive unit cell is face-centered unit cell, also referred to as FCC. One more thing in the previous case, please everybody write down. Primitive unit cell is also referred to as simple cubic unit cell. Also referred to as SCC, simple cubic unit cell. If I talk about face-centered cubic unit cell, in the case of face-centered, constituent particles are present at the corners as well as at the center of each face. Now, what is a face? See, for example, you are standing at the center of your room. The front wall is your first face, the back wall is your second face, the right wall is your third face, the left wall is your fourth face, the top wall is your fifth face, and the bottom is your sixth face. So, basically, if I have to draw the structure over here, this is your unit cell, students, right? First of all, place the atoms at the corners. 1, 2, 3, 4, 5, 6, 7 and 8. The atoms are now present at the corners. Now you are left with what? Atoms at the face center. So this is 1 top, 2 bottom, left, right, 4, 5 back, 6 front. 6 atom at the face center. So this is the structure for face centered cubic unit cell. Now comes your next part, that is your body centered cubic unit cell. Now you are going to observe which one? The body centered one. Atoms are placed at the corners as well as the body center. Okay, so this looks like this. That is basically again a non-primitive one. Why? Because see, the constituent particles are present at the corners, but along with that at the body center. For example, you are standing at the center of your room, that is body center. So let us see now. If this is your unit cell, students, so atoms are placed at the corners like this. Also, atom is placed where? Also, it is placed at the body center. So, this is the structure for BCC, body centered cubic unit cell. Now comes the next type, that is your edge centered unit cell. In the case of edge centered unit cell, students, atoms are present at the, here you can write it down, atoms are present at the corner as well as at the center of edge. So that is edge centered unit cell. Let us make a structure. For example, this is your unit cell, students. You have to place atoms at the corners 4, 5, 6, 7, 8 as well as at the edge centers. Now what are the edges? When two corners join with each other, it forms edges. Okay, that means one will be present over here. This edge 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and at the back here it is 12. See, 1, 2, 3, 4. Join two corners, you will form an edge. 4, 4, 8 and then 2 will be left over here, 2 over here, 12 edges, right? So this is edge centered unit cell. Now comes end centered unit cell. When atoms or particles, you can say, are present at corners as well as at two opposite face centers. Two opposite face centers, that is end centered cubic unit cell. For example, if we have this structure over here, see the atoms are present at the corners, no doubt there are 8 corners. Now they are present at any two face centers. So either top to bottom or left, right or front, back you can do. This is end centered unit cell. Clear everyone? Now students, you are aware of the corners in your home that we have already done this part. Yes, everyone. Now comes students, contribution of atoms present at different lattice site. That means one single atom is touching how many atoms, and in particular one unit cell. What is its contribution? Okay. So first of all, contribution of the corner. See, total basically if I talk about this corner, this corner is being touched by 8 unit cell. So in this particular unit cell, what will be the contribution? It will be 1 by 8. You can draw the structure, you will get to know the answer. As you all know, it is a summary session, ultimate recap session. So I'm just directly writing, letting you know because it is a 3D imagination. So one atom is being touched by 8 unit cells, and in one unit cell its contribution will be 1 by 8. Talking about the face basically, students, see, for example, if I'm talking about the top wall is being touched in this room also and in the above room also. So it is being touched in 2 rooms. What is the contribution of this top wall and this room? 1 only, no, 1 by 2, no, because it is touching 2 rooms. So contribution will be 1 by 2. Let us talk about within the body, that means body centered cell. So we have a, for example, a particle in the center of this room. Is it touching another unit cell? No. So its contribution will be 1. Let us talk about in the case of edge. See, one edge basically is touching 4 rooms. One edge is touching basically 4 rooms. So in one room, its contribution will be 1 by 4. Clear, guys? Everybody please write it down. Now students, comes the most important part, that is number of atoms in a unit cell. Now, what is the formula in order to calculate the number of atoms in a unit cell? Number of atoms in unit cell is equal to total atoms into contribution of one atom in a unit cell. Contribution of one atom in a unit cell. Let us talk about simple cubic. See, in the case of simple cubic, number of atoms is represented by Z. Total atoms in the case of simple cubic, atoms are present at the corners. What is the contribution in the case of corners? 1 by 8. So this comes out to be 1. Let us talk about body-centered cubic unit cell. In the case of body-centered cubic unit cell, atoms are present at the corners as well as at the body center. So for the corners, how many corners? 8. What is the contribution? 1 by 8. Plus, how many body center atom? 1. What is the contribution in body center? Now only we have seen 1. So this comes out to be total, comes out to be 2. Let us see in the case of face centered cubic, the atoms are present at the face centers as well as at the corners. So how many faces? Total 6. What is the contribution in one face? We have already done in the previous slide. It is 1 by 2. How many corners? 8. What is the contribution? 1 by 8. So this comes out to be how much? 3 plus 1 comes out to be 4. Clear, everyone? Yes, very, very important part. Very, very important. Everybody please write it down. Done with this one. Now students, comes your close packing. See, first of all comes close packing in 1D, 2D, 3D. 1 dimensional, 2 dimensional, 3 dimensional. If you are arranging particles in 1 dimension, I am asking you what is the coordination number. You very well know what is 1 dimensional. Either in x-axis you are keeping particles, or in y-axis or in z-axis. So if you are keeping particles in x-axis, let us consider. So it is 1D. For example, if this atom I am talking about, it is being touched by how many atoms? 1 atom, 2 atom. So here coordination number comes out to be 2. What is coordination number? Coordination number is how many atoms are being touched by a single atom, or a single atom touches how many atoms. So in case of 1D, it is 2. Now let us talk about close packing in 2D. In order to see 2D, there are 2 cases. One is square close packing, another one is hexagonal close packing. Let us talk about the very first one, that is square close packing, that is AAAA type. Now see, what you have to do is, this is your A layer, your A layer, your A layer. This is your first layer, A layer. A layer, A layer, A layer. So it is AAAA type. Now what is 2D? X-axis, Y-axis, X-axis, Y-axis. So AAA type. Now see, let us consider this atom. This atom basically is touched by how many atoms? See, this is touched by these 2 atoms. Moreover, this is touched by this atom above and this atom below, guys. So it is touched by 4 atoms. That means the coordination number over here will come out to be 4. Moreover, over here it forms a square. So this type is referred to as your what? This type is basically referred to as your square close packing. Why? Because it forms a square. Also, the coordination number here comes out to be 4 because this atom particularly is touched by 4 atoms. Clear? So this is square close packing. Now comes the second type, that is hexagonal close packing. See the arrangement. Here it is AB type. See, in square close packing it was like this. AAA. First layer is similar to the second layer. It is similar to the third layer. This was a square one. Talking about hexagon, it is like this. If it is your A layer, the B layer will be like this. 2 atoms, then 1 atom. 2 atoms, then 1. 2, then 1. Here it will be like this, 2 atoms and 1, 2 atoms and 1. So this is hexagonal. AB kind of packing. Let us consider over here one single atom, this one. It is being touched by how many atoms? See, it is being touched by these 2 atoms, 2, then above 2 and then below 2. So this forms a hexagon. So coordination number over here is, it is being touched by 6 atom, it is 6. So coordination number here comes out to be 6. Moreover, it forms a hexagon. So it is hexagonal close packing, also referred to as AB type. What it is referred to as, guys? AB type. Clear? This is all about the 2D close packing, students. Now let us talk about the 3D close packing. See what happens in the case of 3D. In the case of 3D, you shall be obtaining 2 kinds of packing. One is again your cubical close packing, and one is your hexagonal close packing. Now you will say, ma'am, hexagonal we have done in 2D also, but yes, it is in 3D also. So if you are forming AB kind of arrangement, it is hexagonal close packing. If you are forming ABC kind of arrangement, it is cubic close packing. Okay. So let us start. It has a coordination number 12 in the case of the close packing in, I am talking about 3D, that is HCP. So it is, in the case of HCP, you can even mention it has a coordination number of 12. Moving on to the next one. Here you can see this is arrangement of particles. A layer, then we have B layer. So when we are arranging particles in such a way, we are forming an HCP structure. We form different voids are being observed. Now what is void? Void is basically the empty space that is found when atoms are placed close to each other. So over here when we are placing them, we find 2 kinds of voids. One is tetrahedral void, another one is octahedral voids. No need to worry in detail. We are going to study about them also. Just wait for a few more minutes. Okay guys? So this is both kind of packing that I am talking about. One is hexagonal packing. Now in the case of hexagonal packing, it is AB kind of arrangement. For example, let me tell you. See, for example, this is your A layer. This is your hexagonal close packing in 2D. First make hexagonal close packing in 2D. This now completely is your A layer. Not consider AB, no. Now this is completely your A layer. Okay, now let us talk about the B layer. See, B layer will be put on the voids like this. Now again, when you are placing the next layer, it will be same of A layer only. Same. Just same as A. Atoms will be placed just same as A. So this is AB pattern, which is hexagonal close packing. It looks like this. It basically looks like this. But when I am talking about cubic close packing, let us consider this is your A layer. Now see, over here the atoms firstly are arranged like this, just similar to the above one. But now comes one more layer. Over here you are arranging particles over here. So this is ABC packing. All of the 3 layers are different. So this is ABC packing, the cubical close packing. Clear guys? Now this structure you can clearly observe, ABC packing. Now comes voids and its types. See, we classify voids. Voids are what? Voids are the empty space that are found when atoms are packed close to each other. There are 4 kinds of voids. One is trigonal void, second is cubical void, third is tetrahedral, fourth is octahedral voids. So one by one, students, we are going to understand about voids. If you want to write voids, this is an empty space found when atoms are placed close to each other. See what happens in the case of trigonal void. Atoms are arranged like this, 1 at the top, 2 at the bottom. So when you are joining them together, here is this empty region that you observe. So this is triangular void. So why it is triangular? Because when you join the centers of these 3 atoms, it forms a triangle, and the empty space is inside this triangle. So this is trigonal void. If you keep an atom over here, you will write its radius as smaller, and the radius of the bigger atom will be capital R. So you are going to calculate the relationship between the void's radius and the atom's radius also. How you are going to calculate the radius of void? You are going to keep a small atom over here and you are going to calculate. Let us talk about tetrahedral. How do tetrahedral void looks like? 3 atoms placed just similar to trigonal, and 1 atom at the top, and 1 atom at the top. So over here, if you are going to observe the space, that is basically your tetrahedral void. Let us talk about octahedral. See, in the case of octahedral, we have 2 cases. 2 at the bottom, 1 at the top. Now, 1 at the bottom, 1 at the top, 2 at the bottom. Either this way, or there is one more way. 4 in the same plane. 4 in the same plane. 1 at the top and 1 at the bottom. I am making it with dotted. So this is again octahedral one. You can even make it like that. Let us talk about cubic. In the case of cubic, 4 in the same plane and 4 atoms placed at its top. 4 atoms placed at its top. So this is cubical voids, the empty space that are found when atoms are placed close to each other. Moving on to the important type, the voids in FCC. We observe that two kinds of voids are seen in the case of FCC, that is basically tetrahedral and the octahedral. You should know the position of both of them. See, basically total 8 tetrahedral voids are being observed, and where are they found? They are basically present at a distance of root 3a by 2 from each of the corner on the body diagonal. So if I talk about total tetrahedral voids, they are basically 8 in number. And if I'll talk about the octahedral void, students, octahedral voids, 1 at the body center plus 1/4 on each edge center, 1/4 on each, how many edges? 12. So this comes out to be 4. So octahedral void, this is octahedral voids, comes out to be 4, tetrahedral comes out to be 8. Always remember, octahedral basically is half of tetrahedral, or in other terms, octahedral is basically twice of tetrahedral, and tetrahedral basically, see, I have to write it again. If you have to find tetrahedral void, you have to do twice of octahedral. So this is what I meant to say. Sorry for the confusion, okay? So tetrahedral is equals to twice of octahedral, and if you have to calculate octahedral, you have to divide it by 2. Clear? Now students, these are the locations that they have clearly mentioned you. Now comes ionic solids. Now comes what? Your ionic solids. Ionic solids are formed between cations and anions, students. So let us understand about them. In ionic solid, there are two types of particles, that is cations and anions, that we really very know. Okay, no need to worry. We have done voids now. Voids radius ratio is coming. So I am going to complete that there only. No need to get confused. Coming back over here, I told you that in ionic solids there are two types of particles, one is cation, another one is anion, and in them basically the types of void that we have to calculate in the case of ionic solid is determined with the help of radius ratio. If we have to calculate the radius ratio, always see radius ratio is equal to radius of cation by radius of anion, or radius of void by radius of atom, right? So you can say radius of cation by radius of an ion, or radius of void by radius of an atom. By this way you can calculate the radius ratio, students. Greater the radius ratio, larger will be the size of cation and hence the coordination number. So this table you need to remember, always you need to remember this table. If the values lie between 0 to 0.155, it will have coordination number 2, it will have a linear structure. If the value lies between 0.155 to 0.225, coordination number will be 3 and the structure is triangular. If the value lies between 0.225 to 0.414, coordination number will be 4 and the structure will be tetrahedral. If the value lies between 0.414 to 0.732, coordination number will be 6 and the structure will be octahedral. Then, and if the value is between 0.732 to 1, it is coordination number is 8, it is cubic, and if it is 1, coordination number is 12, it is FCC and HCP, right? Everybody, you have to learn this table out, yet very important part. Yet is very important part. Clear, everyone? Now students comes different types of crystal structures of some ionic solids. First one is rock salt. First one is rock salt, also referred to as NaCl. Also referred to as NaCl. Okay, over here they have told you the position, their coordination number and number of formula units. So in the case of NaCl, Cl negative forms a CCP and Na positive is present at all the octahedral voids. Do remember, example they have already given you. You need to remember that Na positive and Cl negative has a coordination number of 6. Students get confused and mark it as 4, but it is wrong. The coordination number is 6, guys. Now comes number of formula units, it comes out to be 4, right? Talking about CSCl, again yet most important one, these two are important, even zinc blende is important. CSCl type, Cl negative ions are basically present at the corners of the cube and the BCC structure, while Cs plus ion is present in cubic void, okay. This question is generally asked, Cs positive and Cl negative has a coordination number 8 and number of formula units is 1. Talking about zinc blend, what is zinc blend? It is ZnS. Talking about zinc blend, Zn plus 2 basically are present at alternate tetrahedral void and S2 negative. How is S2 negative written? It is like this. It is present in CCP. They both have a coordination number of 4 and number of formula units is also 4. If I talk about fluoride structure, now what is fluoride structure? It is CaF2. So in the case of fluoride structure, Ca+2 forms CCP, F negative is present in all tetrahedral voids, and coordination number is also again yet asked in the examination that Ca+2 has a coordination number of 8 and F negative touches 4. Last is anti-fluoride, so you can learn the value, students. Clear everybody? Please write down this table so that we can move on to our next part. Done, guys. Now students comes effect of pressure and temperature. See, on increasing pressure, the coordination number increases. For example, if we have NaCl structure, its coordination number will increase if we are increasing pressure. Its coordination number is 6:6, so it will increase into CaCl. That means 8:8. Clear, guys? Now, on increasing temperature, always remember coordination number will decrease. What is coordination number? How many atoms are being touched by a single atom, right? Coordination number will decrease. So CaCl structure will convert into NaCl structure, that is 6:6. Clear? Coordination number will decrease. So this is the effect of pressure and temperature, guys. Clear, everyone? Now students come packing efficiency. What is packing efficiency? How efficiently you are packing a particular atoms in a particular crystal lattice. How you are going to calculate it? See, students, packing efficiency basically is equal to the volume of atoms in a unit cell, the volume of atoms present in a unit cell divided by total volume of unit cell into 100. So basically this is going to be the formula for packing efficiency, everybody. This is going to be the formula for packing efficiency, everyone, right? Moreover, if I'll ask you about packing fraction, so packing fraction is packing efficiency divided by 100. So that is packing fraction. If I ask you what is void, first of all you will calculate packing efficiency, that yes, it is occupied in this much space, so the leftover space is void. So you will subtract packing efficiency from 100, you will get the percentage of void. Clear, guys? Now this is the value that you need to remember. Here it is calculation involving cell dimensions. See, first is types of unit cell. It is SCC, BCC, FCC. SCC is simple cubic unit cell. BCC is body centered cubic unit cell. FCC is face centered cubic unit cell. So, in the case of SCC, the coordination number is 6. In the case of BCC, the coordination number is 8. In the case of FCC, the coordination number is 12. Packing efficiency for the case of SCC that you are going to calculate. See, now as I have already told you, this is ultimate recap session, ultimate summary session. So, I am not writing the complete calculation, just writing the value so that you can learn, because direct questions and competitive exams are seen. So, in SCC, the packing efficiency is 52.4%. In BCC, it is 68%. In FCC, it is highest, that is 74%. Now comes the relationship between A and R. What is A? A basically is your, I'll write it over here. A basically is your edge length of the unit cell, and R basically is your radius of atoms placed on the lattice. So in the case of SCC, it is 2R is equals to A. Edge length of a unit cell is equals to 2R. In the case of BCC, it is 4R is equals to root 3A. Right? And in the case of FCC, it is 4R is equals to root 2A. Clear, guys? Everybody please write it down. Everybody write it down, yet very, very important part. Most of the questions are just observed from this particular segment. Now students, one more calculative segment from which question can be asked, that is about density. How are you going to calculate density? So in order to calculate density, density is equals to Z into molecular mass divided by Avogadro's number into A cube. So this is basically the formula of density. Let me tell you what is Z over here. Z is number of atoms. Z is number of atoms in a unit cell. In a unit cell, what is mm over here? Mm over here is molecular mass. Na over here is Avogadro's number. A over here is edge length of the unit cell, right guys? So by this way you can calculate the value of density. If you don't know the value of Avogadro number, it is 6.023 into 10 raised to the power 23. Clear everyone? Now this ends our calculative segment. Now comes our last topic, that is defects in solids, or I would say the imperfections in solid. See, why imperfection arises? Imperfection can arise due to the replacement, displacement or misplacement of an atom from the crystal structure. Okay. Now, it can be seen in a line, it can be seen in a plane, it can be seen at a point. So, when at a point there is any defect, that is point defect. When there is a defect in a line, that is line defect. When there is a defect in the plane, it is plane defect. Now, defects are further categorized into three types. The very first is stoichiometric defect, second is impurity defect, third is non-stoichiometry. Stoichiometric defect is that defect in which the stoichiometry or the number changes of the particular atoms. Number refers to as the stoichiometry, the particular arrangement. If I talk about impurity, in here impurity you may observe, in the case of, I will tell you in detail what it is exactly. In non-stoichiometric effect, there is that the stoichiometry basically changes, the value basically changes. For example, Fe 0.980, okay. So basically the number basically changes, the complete stoichiometry of the compound changes. We are going to start with the very first one, that is the stoichiometric defect, also referred to as intrinsic effect. Intrinsic defect, okay. The very first is vacancy defect. In the case of vacancy defect, a vacancy is created, an empty space is created. So when an empty space is created, density basically decreases because the number of particle decreases, right? So this is vacancy defect. Now moving on to the next type of defect, that is interstitial defect. It is observed when an atom basically is present at the interstitial sites. What are the interstitial sites? It's the sites that are present in between. For example, if we have AB pattern, if the atom comes and stands in between, that is interstitial. So when an atom is present at interstitial site, so that is interstitial defect. Here density will increase. Why? Because number of atoms are increasing as there is one more atom present at the interstitial site. So this is interstitial defect. Next comes is your Frinkel defect. Now what is a Frinkel defect? In case of Frinkel defect, smaller ion dislocates itself to interstitial site. That is a Frinkel defect. Now what is smaller ion? Basically cation moves to the interstitial site. Cation moves to interstitial site. Now this is an example of ZnS, AgCl and AgBr. What will be the effect on density? Density will remain same. Also, this is a dislocation effect because an atom moves from one position to the another one. It is dislocated. So, it is again a defect. This is dislocation defect or Frinkel defect. Moving on to the next one is Schottky defect. What it is exactly? It is basically Schottky defect. It is seen in NaCl, KCl, CSCl. In this, equal number of cations and anions are missing. Equal number of cations and anions are missing from the crystal lattice. See, if two positives are missing, then two negatives are also missing, right? So over here density is going to decrease. I guess you very well have written the examples also over here. Now students, comes the next kind of defect, that is basically your non-stoichiometric effect, when there is a change in the stoichiometry. So here it is metal excess defect. Now metal excess defect can occur due to anion vacancy, and due to extra cation. Anion vacancy is when a negative particle moves away. So there will be more amount of positive particle, that means metal will be excess. Or when there is an extra cation in the interstitial side, that will also cause metal excess defect. So it changes the number, no, that is non-stoichiometry. Then students, one more key points you need to remember. There is also one more, that is metal deficiency, when there is less amount of metal, okay. Key point is basically that NaCl appears yellow in color. Yellow color in NaCl is due to metal excess defect. Why? Due to which reason, students? Due to metal excess defect, due to which unpaired electrons occupy the anionic site. See what happened when there is a metal excess effect, there is an unpaired electron that comes to the F center. In the case of NaCl, an atom comes to the F center, electron basically comes to the F center. When it comes to the F center, it will impart some color. So that's why these are yellow in color, and those sites are F centers. These unpaired electrons absorb some energy from the visible light for excitation that makes the crystal appear yellow. So it is very, very important part. Moving on to the next one, now we have types of solid based upon the electrical properties. Based upon the electrical properties, we do classify them as conductors, semiconductors and insulators. Conductors, semiconductors and insulators. See, in the case of conductors, there is no space between the conduction band and the valence band. So electricity is conducted easily, electrons can transfer from one to another. In the case of semiconductor, there is a very small gap between the seen between the valence band and the conduction band. But in the case of insulator, students, there is a very large gap that you are going to observe between both of them. There is a large gap due to which they are unable to conduct electricity. So these are the types of solid under the basis of electrical properties. Now students, let us understand the doping process. See, this is basically the classification of semiconductor further. See, semiconductors are further classified into intrinsic and the extrinsic one, right? And the extrinsic one are further categorized into N-type and the P-type. So basically this is your N-type semiconductor and this is your P-type semiconductor. N-type, why it is referred to as N-type, let me tell you, because there is an extra electron over here. What do? You are going to dope silicon and germanium doping. Doping is addition of impurities. So silicon and germanium doping is done with either phosphorus or arsenic. So you are doping group number 14 with group number 15. When you are doping, you will find an extra electron. This extra electron is responsible for imparting negative charge, and so it is N-type semiconductor. And when you are doping silicon and germanium with group number 13 elements, for example boron or aluminium, it will have one hole over here, not electron, there is a hole present over here. Hole is formed over here, which imparts basically your positive charge, so it is P-type semiconductor. Clear, guys? Now students, coming to the last part, that is magnetic properties of solid. Always remember, solids are classified into diamagnetic, paramagnetic, ferro, ferri and antiferromagnetic based upon the magnetic properties. So diamagnetic is basically in which all electrons will be found in the paired form. There will be pairing of electrons, right? That is seen in the diamagnetic. In the paramagnetic, there is presence of unpaired electrons. Clear? Also see that in the case of diamagnetic, it is weakly repelled by external magnetic field. And in the case of paramagnetic, it is weakly attracted by magnetic field. Let us take the examples. In the case of diamagnetic, NaCl, KCl are the example, and these are the examples in paramagnetic. In the case of ferromagnetic, you can see permanent alignment. In a single lane alignment is being observed in Fe, nickel, cobalt, okay. Now, in ferrimagnetic, unequal number of alignment. 2 are at the above, 1 at the bottom, 1 at the above, 2 at the bottom, unequal alignment, Fe3, 4. And the case of antiferromagnetic, compensatory wavy form is being observed. 1 at the top, 1 at the bottom. So, MNO is the example, yet again the important one. Clear, guys? So, yes, my dear students, we end our today's session over here. Now, in this particular session, we have completely finished our chapter solid state. And I now very well know you are aware with each and every terms, with each and every topic that is very, very important to you. Now, what is your work? Your work is to revise. We have already revised this in this ultimate recap session. The very first chapter is completely done. Now, what is your role? To revise the chapter and to apply all of the topics onto the questions. So, now it's your work to practice practice questions, and we will be now meeting in the next session with the next chapter of ours. Till then, students, keep smiling, keep learning. Thank you so much and have a good day, everybody.